And I want to announce the next speaker, who is a co-founder and CTO of Subspace Labs. And he's going to touch one of the key problems that we have in blockchain, which is transactions per second, of course. He's going to talk about the subspace road towards 1 million plus transactions per second. Welcome, Nazar. Hello.
Hello.
It's nice to have you here, Nazar. How you doing?
Thanks for having me. I'm great.
Yeah, basically your talk.
Yeah, I think everyone is aware of Web3 is the future, and we want and we expect more and more apps to be on-chain. And that basically requires not only the current blockchains that are pushing the capabilities of the blockchain technology, we actually need something that can run truly at the internet scale. When we are talking about like Web 2 kind of sense of internet scale. And I was trying to withdraw some funds from exchange a few days ago using the fastest blockchain in the world, according to their website. That's a quote. And I was not able to. I was waiting for 6 hours and it was canceled due to congestion. So there's clearly 6 hours and it was canceled. I wasn't able to. So there's clearly a problem that needs to be solved, and we are trying to tackle that from some of the angles.
Well, I'm excited to hear your talk, and I'm passing the microphone to you. And
okay, a little bit about me. I'm Nazar. I'll be entertaining you for the next 30 minutes or so. I'm writing blockchain at Subspace Labs. You can find me most often on GitHub. As I said, we are trying to build a blockchain that can run actually at internet scale, and that basically means that we need more transactions per second as much as possible, so that every user on the internet can use Web3 application and do not distinguish that from Web 2 as inferior performance. There is a short plan for today. We'll start with some background, then we'll dive deep into the aspects of the WASM runtime that might impact performance, both for pallets and for smart contracts as well. Then we'll go into some challenges specific to smart contracts for pallet contracts and Substrate specifically, with a bunch of nuances that make fast smart contracts a non-trivial task. Once that is done, we are with internals, we'll look at the blockchain from the other side of the stack, how transactions are generally scheduled for execution, what opportunities for improvements there are, and how we can leverage some of the vertical scalability techniques to achieve higher performance on a single blockchain node. And then we'll talk about scaling that single chain performance horizontally with sharding a little bit. We'll conclude with some simple math and funny numbers based on the public information that is available online that you can check, that will give us an idea of what kind of performance we can achieve if we apply all of those tricks together. And in the end, we'll hopefully have some time for questions. All of this is based on some extensive research that me and our team were doing, following upstream work of Substrate and Ink, and I hope you will find this information useful. And there will be a bunch of links throughout the presentation if you want to follow something more specifically in more detail, and the presentation will be made available for you after the talk. So before we dive into how blockchain looks internally, we need to understand some of the fundamental limits of physics that we cannot bypass and we should strive for on the other hand. In ideal blockchain, we would utilize all of the bandwidth available. We'll work at the network latency propagation delay. And we'll also use all of the CPU cores, RAM, GPUs available, and will probably be bottlenecked by random access on the disk subsystem in the end in practice, in most cases. However, when we are looking at the existing live blockchains, they're typically not utilizing all of that. They're only utilizing a fraction of it. And coupled block authoring and execution limits bandwidth utilization, for instance, because if you increase the block size beyond some optimal value, it leads to increase in propagation delay, and that increased means increase in forking and so on. And decreasing block time, again, leads to increasing forking and decreasing security. We cannot just decrease it arbitrarily and infinitely. And it is still a big challenge for blockchains nowadays to utilize more than one core for transaction processing, let alone taking advantage of something like highly parallel GPU capable of processing thousands of transactions or some thousands of different separate threads of work at the same time. And a situation around storage also becomes more and more challenging, especially when we are talking about history of the chain as the number of transactions increases and the history grows faster. But also it is performance-wise, because the more random reads and writes we are doing, that exceeds basically the limitations of the hard drive or SSD. But it doesn't mean that we cannot get closer to those limits. And there are some papers linked below that basically describe how we can overcome some of these limitations if you are interested. And basically what they're doing is they are taking Bitcoin, the standard Bitcoin blockchain, and they recognize that there are several parts to it. And if they decouple those parts and scale them independently, they can actually achieve something like 10,000 times faster Bitcoin with the same security guarantees and the actually improved latency at the same time. So it's certainly possible. Now we're going back into the WebAssembly. We have this WebAssembly language, which is basically a language for an imaginary computer. It cannot run directly on the hardware. It needs some kind of engine to run it. And there are different flavors. They have different trade-offs to them. So interpreter is relatively simple one of the bunch. It just reads and executes instructions one by one, meaning that it doesn't have to do much preparation before it can start executing the code. It has predictable performance, which is great, but the performance is actually like 1-3% of the native machine code, which is not particularly impressive. Ahead-of-time compilers are great because they can achieve performance which is about 50% of the native, and sometimes even higher depending on the use cases. However, they usually take much longer to compile, and that compilation time is not always constant. So it's harder to predict in some of the instances comparing to the interpreter. And gypped compilers, they are kind of a strange combination of both, because they can start as an interpreter, but they can also switch to the compiled code when the engine determines that some piece of the code is actually performance sensitive, and it can just swap the code on the fly and make a trade-off that way. But again, the compilation time is kind of, it can be different. It's not deterministic. So for the runtime in Substrate, the choice is to use ahead-of-time compiler, because the blob from which your pallets compile to, it is basically trusted in a sense that the authors or like the committee on the chain decides what can be deployed, and that way we can be sure that the problem, which is called a JIT bomb, where you produce a code in WASM in such a specific way that it tricks compiler into a special situation where it takes much longer to compile than it would have otherwise, basically making the compilation time very long. This is less of a problem in the runtime because that code is trusted, so we can actually rely on the ahead-of-time compiler, and in case of Substrate is WASM time, that compiles that, and then it can also cache that precompiled code because the code is running every block. So there is a lot of code reuse that can happen to actually improve the performance of the stain, to not recompile it every time we have a block. And also, in order to limit how much work will be done every block, there is a resource tracking which is implemented using weights. Again, because it's trusted, we can trust pallets that they will provide correct weights, or rather the runtime will inject correct weights for those particular calls. And then we can basically restrict how much space or how much work we want to do per block to limit the time or limit the size of the block. And that way we can have predictable performance. We can make sure that if the block time is X, we can make sure that the work can be done in the time X on the reference machine that we've benchmarked our weights against. And in order to improve performance, we can actually use several things. We use host calls for native features, those features that are physically not possible to implement in the runtime. We're just calling to the client outside of the runtime to do something like storage. Or we can also offload heavy computation if you're talking about crypto, especially elliptic curves, hash functions, that kind of thing. Those things are usually done, again, on the host, and that improves performance. If you want to improve performance on top of that, which is probably possible, you can introduce more host calls if you want to offload heavy computation. For instance, you can verify ZK proof on a specific curve, and that is great, but you need to remember that every time you add a host function, it's not free. First of all, your client will have to have to support that host function basically forever, because if you're syncing chain from Genesis later, the old runtime might still use that host call, even though your new runtime doesn't care about it anymore. So just be very, very careful about that. And otherwise you can break your chain. And also note that there are many useful primitives already available. They are in SPIO crate in Substrate. So take advantage of that and get your runtime faster. Also benchmark your runtime. Sometimes approaches that lead to faster native code, like monomorphization, could actually be more expensive than dynamic dispatch in WASM. For instance, boxing of big structs in pallet calls or using references actually will lead to smaller and faster WASM code, and that then sending data structures by value around, and that will be better in terms of performance. There is also another kind of smart caching which you can do for smart contracts with the WASM single pass compiler. For popular contracts like in Ethereum, it's observed that there are many, or like not many actually, contracts which occupy most of the gas. So if you can precompile some of those, it will be faster on the pallet-contracts level, but we'll talk about that a little bit later. Going to the pallet-contracts, it's a completely different environment. By default, for WebAssembly, we use IncDSL, but there are also other options. And it shares some of the features or some of the specifics with the runtime, like host functions for different heavy or native things, but it also has some differences. So one of the first challenges is it goes from the fact that the code is user provided, meaning that anyone can permissionlessly deploy this code to the blockchain and cannot be considered trusted. So that leads to the problem where ahead of time compiler is generally not applicable because it doesn't have predictable compile time, and if you have a very limited time for the block execution, you don't really want to have unknown amount of time per call occupying your block time, right? You really want to have predictability, and you need to do gas metering to actually stop execution at a certain time if it exceeds the gas. Otherwise, you cannot just do static waits again because the code is not trusted. So by default, pallet-contracts uses WASM interpreter written by Parity. And what makes things even worse is that WASM interpreter, which is slow as we described before, it actually is compiled to WASM, and it is running under WASM time in the runtime. So we kind of have a very small performance fraction from even smaller performance, which is really not great, as you can guess. But there is a work ongoing to use WASM single pass ahead of time compiler, which is non-optimizing. It generally is faster at running compiled code, and it takes also a little bit more time to prepare WASM beforehand, but because it doesn't have any optimizations, it is actually constant time in terms of how much time it takes to compile, which makes it more suitable for the pallet-contracts. However, when we measure the end-to-end time, it turns out that actually the performance is kind of comparable or even worse than with WASM, which is unfortunate, but I think there will be more improvements on that in the future. And also caching is not efficient for these contracts either, because we have many more contracts than we have pallets, and we cannot necessarily use the same approach as we do with the runtime, where we can have several instances of the runtime. We can cache several versions of the runtime if necessary, if we do runtime calls to make things efficient. We basically need to optimize heavily for the startup latency that dominates execution time in many cases in practice. And in some cases, it turns out that the more complex code is actually worse, because in case of Inc 3.0, there were actually many smart, lazy data structures removed from the code base. The idea behind those was to minimize the state access, because that was considered to be a big chunk of like the cost of transaction processing. And it was a sound approach on the surface, and it should have resulted in faster code. However, in practice, it turned out to be actually slower because there are two issues with it. First of all, smart data structures mean a lot of code to actually make them smart. And that means bigger WASM bundle. And then bundle means that there is actually more resources spent to compile it and to prepare to interpret than would have been otherwise if you have a smaller contract. which increases latency for startup. And also, on the other hand, sophisticated data structure means that there is a lot of branching in the code. And branching in the code means that there is a lot more gas metering that needs to be happening. And that actually means that even though the gas price is lower, the absolute time of that smart contract execution in practice is actually larger than it was before. So it's kind of counterintuitive how that works. However, because the gas metering was done with the host calls, that was leading to worse contracts, and that's why it was removed. And I found that that situation personally kind of funny because it was trying to be smart, but actually the simpler approach appears to be better. And then the big problem with gas metering as well, that's like a big topic for smart contracts. And in various VMs like EVM, and WASM is not an exception. And most of the research actually that is searchable online compares eWASM with EVM, not just generic WASM smart contracts. And there are several gas metering techniques which are generally implementable for smart contracts. The first one is native to the virtual machine. So that's EVM or WASM middleware, where the VM itself knows how to handle that. And native instrumentation is great because it's fast. However, in both Near and Substrate, for instance, that want to be VM agnostic, they are looking for a generic solution that can be applicable for any VM regardless of what you are using today, so you can swap it later. There are two ways how to do that. Basically, how Substrate works today, it reads through all of the WASM that you have. It identifies parts of the WASM which are non-branching, and it basically charges you for that non-branching part right away. And then it makes a host call to like charge the actual like value. And then every time it meets a branch, it actually does that again. So that's why the previous approach with the Ink before version 3 was expensive, because there was a lot of branching in that caching code. However, in Near, they've actually improved the situation, and Substrate will be doing that in the future as well, from what I understand. You can actually instrument WASM in such a way that you don't need to do host calls because of some of the guarantees that WASM has internally in terms of memory layout. So you can actually have a counter within WASM memory instead of that, and you can just increment that counter in memory, and you can have much better performance because you're not paying the host calls, which are relatively expensive. So on one hand, you can like save some resources if you're doing something really heavy. On the other hand, if you're doing that very often, that is kind of it goes against you basically. And then we can step back and look, and we can look at like what is the baseline, like what we can expect if we run Substrate node more or less out of the box. And I found this series of tweets from Gavin from a few years ago. I think everything got better since. That we have about 1,500 transactions per second, and that is great. But that only gives us about 600 times apart from 1 million goal that we want to have, according to this presentation anyway. And that is a lot. But if you're actually trying to run that benchmark yourself, you'll probably recognize that the node is actually not running at 100% CPU time utilization all the time, which is interesting. So what does it actually spend time on? And it turns out there are actually 3 big chunks, like slices of time that go into the block time that we know. The first one is block authoring. So we are collecting transactions from transaction pool, we are executing them, we put in the block header together, signing it, we created a block. Then we need to propagate that block over the network. And then once someone receives that block, they actually need to run it almost the same way that block author does before they actually can build a new block on top. And you can recognize that most of the time nodes are actually not running transactions. Most of the time they're actually waiting for something. But it would be really, really nice if they actually did do something, right? So this is where decoupled execution comes in. In standard blockchain, we have several different things that nodes do. They propose new blocks. We've discussed that. They verify transactions, okay. They maintain blockchain history, and they also maintain state. So they like apply transactions one by one. They apply this history, and they end up with some kind of snapshot of that state as a result of transaction execution. So what we recognize in Subspace, based on some of the papers, is that we can actually split that between 2 different kinds of nodes. And farmers, consensus nodes in our protocol, can be responsible for proposing new blocks and maintaining the chain history. So they will maintain the history of the blocks. However, they will not run transactions. Staked executors will actually verify transactions that as they come in from users, and they will maintain state, the result of application of those transactions. So farmers don't have to spend so much resources on that in terms of computation, and executors don't have to bother themselves with storing all of the history, which is great. In Subspace, we actually apply a technique similar to how it's described in the PRISM paper linked earlier, where we split these responsibilities very specifically. And in our case, farmers are responsible for safety of the protocol, for the consensus part, and executors, they're responsible for liveness, how much time it takes for transactions to propagate. So what happens is users submitted transactions to executors. They verify that those transactions are actually valid. They can pay for the fees, for instance. And then they will combine those transactions into bundles. Transaction bundles are just a collection of transactions. It's not a block. It's just a collection of transactions that executors put together. And since they are staked, they're just signing that, certifying that they verified something like fees for those transactions. After that, they send headers of those transactions to consensus nodes to farmers that produce in blocks, and they send just the header. So the header is much smaller than the transaction. Let's say transaction bundle can be 0.5 MB, and the header is like 300 bytes. And those headers are what farmers will include on-chain on their side. And they will just reference transaction bundles, and they will use data availability sampling if necessary to ensure that those headers actually correspond to something that exists out there and not just some random data. After that, executors will observe those blocks that are produced by farmers, and they will take all of those bundles mentioned in that particular block, and they will run them, and they will produce a state update on their side. So executors are maintaining state, farmers are maintaining history, and then once that execution is done, they will submit execution receipt back to the farmer, committing to that execution. Execution is fully deterministic, so executors do not really have any leeway whether this is right, this is wrong. Everything that is included in the farmer is correct, and they have to execute it. There is one and only one correct way to do that, and they should do exactly that. If they are not doing that, or they are submitting incorrect bundles, there is a fraud-proof mechanism where they can be slashed because they are staked. Farmers, on the other hand, are completely permissionless, like in BitConsents. They can come and go, and there is no penalty for being offline. This decoupling basically means that farmers and executors, or farmers, can produce blocks at their own pace. They can produce relatively small transaction bundle. They can include small transaction bundle headers, and that results in a low overhead and opens possibility for mass participation in the consensus, because that's great. And we can have we're having over 25,000 consensus nodes on our non-incentivized testnet a few days ago, and today we launched incentivized testnet. So we expect even more nodes once there is some incentive to actually participating. While executors, they can pack megabytes and megabytes of transactions into those bundles that farmers do not have to see, and they can run kind of in parallel to farmers, and they can occupy their CPU time basically 100%. So we can reclaim all of that wasted wait time that we've seen on the previous slide. So what does it give us? It basically means that on those previous slides, we were having a 1,500 transactions per second over 3 seconds block time. So if you are saying that that is 3 seconds, 1,500 per second, 4,500 transactions per block time, but now we can do the same per second if you are assuming that execution took about a third of that time roughly. So 1/3 for block authoring, 1/3 for propagation, 1/3 for the block import. And we can compare that to some of the other networks. So on Ethereum, it's 15 transactions per second, not great. On the Near, they estimate that at 1 million nodes, they can have so many shards, so they can process 100,000 transactions per second. And in Solana, they can process theoretically 710,000 transactions per second if transactions are very small, 176 bytes, and the bandwidth of every node is 1 gigabit per second, which is kind of optimistic if you want mass participation. But in the result, it's kind of meh, because we are still 200 times away from 1 million transaction per second goal, and we actually would like to do better. And we can apply some of the traditional techniques from Web 2 world. If you are getting to the point where we can no longer run more things on the same core, why don't we use multiple cores? On modern machines, you have at least 8 cores or at least threads in the worst case. And there are several approaches how we can do that. So the first one is speculative execution. This is something that was tested on Ethereum. The latest and most interesting one is from Microsoft Research about Forerunner, where they've actually achieved speculative execution of unmodified Ethereum node with about 8x end-to-end performance improvement. That basically means they can improve the performance. They can process 8 times more transactions per second, or they can potentially utilize 8 cores instead of 1 to do so. The other approach is explicit. This is kind of what Near and Solana are trying to do, where they have a different model for accounts, and they basically make it clear for the executor on chain to see what transactions will be potentially conflicting and which will not. So the executor can basically build a DAG and run transactions which are not conflicting in parallel at the same time. And that way they can exceed performance of a single core very easily. And that way they can achieve higher performance. And if we apply that, we assume that we have 8 cores and we can saturate all of them at the same time. That means we have about 36,000 transactions per second, which puts us about 27 times apart from the goal of 1 million transactions per second. So we kind of, there should be still something we can do. And this is still kind of considered to be a vertical scaling on one side because we are still dealing with the same machine. However, we can actually go into horizontal properly. In most sharding designs, number of shards is on the order of tens of shards, which is typically caused by degrading security and increasing complexity in the sharding mechanism that they have. However, in Subspace, due to the coupled execution nature of the protocol, we can actually implement some nice tricks that do not require sacrifice in security and safety of the shards when we are adding more. So the insight there is that all of the shards that we have that farmers are maintaining the history of can actually be composed into the global history of the all blockchains as a network as a whole. And then farmers can actually store that history cumulatively, and they can solve on that global history and use that for farming and for plotting. And once they win, they will actually apply cryptographic sortation to figure out which shard they actually won on. And then they go onto that shard, quickly, and they produce a block there. So that means that all of the history of all shards is tied together, but in the end, we have one history and we have one set of farmers. So our security as we add shards doesn't decrease because all farmers essentially solve on all of the history and all of the shards all at the same time. It's not like in proof of stake where you have certain limited amount of stake and then need to slice that stake between different shards, right? On the other hand, our executors are completely decoupled from that. They are not responsible for safety. So there is no need, like in proof of stake protocols, to actually make them rotate all the time actively across different shards. They can stay in whatever shard they want, and there is this paper called Free to Shard where there is a mechanism how they can assign themselves to different shards and detect malicious behavior and fix that behavior automatically. And that way we can allow executors to do as much work as they want on whatever shards they want. And in that sense, we can have, we are currently have a working number of 65,000 shards, which is unusual for most people, I think. But it actually is something that could work. And if we take that into account, this is the kind of ratio that we are away from our 1 million transactions per second. We can actually observe that this is more than 1 million transactions per second by quite a lot. So if you flip it around, we can have theoretically over 2 billion transactions per second on the network as a whole, and we can have something like 6 terabits per second of upload bandwidth if you assume that every node is just 100 megabit, has 100 megabit per second connection on the executor side, not even on the farmer side. That is, of course, an upper bound. It doesn't mean that the network will run at 2 billion transactions per second, but if we are even 1,000 times off this target, if let's say our execution is not as fast, or we are using just 1 or 2 cores, or our number of shards is not this large, It's kind of obvious that if you are trying to approach the physical limits of the network and resources, we can actually get pretty damn close to that. And with this architecture, 65,000 shards is just like an arbitrary number. It is not a fundamental hard limit. It can actually increase as number of executors increase, and we have more farmers to store the global history of the blockchain. And with that, we have a consensus white paper on the website. We have some text summary, and we are also hiring. And I would like to answer some of the questions from the audience.
Thanks for the talk, Nazar. Yeah, it was really, deep dive. And what I think of is that the more people we have, the more speeches we have, the more like new approaches, and the more people, the more new approaches and interesting approaches to the problems. Like, for example, make the blockchain multi-threaded. That's interesting. And yeah, I like what you shared. And we have a couple of questions, and one is from Green. He says that your model looks similar to Celestia, but you also have proof of storage. What are the benefits of your approach, and why is it better?
There are several different blockchains which are trying to do something similar. I think in our case, the primary insight that we have comparing to many other blockchains is that we are a proof of space, which is like a broad general category of blockchains that are dealing with space. We are also proof of replication, which means we are storing some useful space, not just random data. And we are like even narrower flavor of that, where we are storing the history of the blockchain itself. So fundamentally, we are solving some of the incentive challenges in the protocols, where let's say you have a node running and you dedicate some space to the protocol, and then you need to choose, do you want to store the history or you want to maximize your profit? This goes a little bit into like consensus part of our protocol, which I didn't cover in this talk in much detail, but that is like the biggest kind of differentiation I think that we can do. And from that, we have this decoupling of consensus, and then there are other nice things that flow from that.
Thank you. That's a good answer. Another question we have from Anonymous: what is the incentive model for running a node?
Right, so we have two categories of nodes. There are farmers and executors. Farmers are producing blocks and they get block rewards, and they also get storage fees for storing the data because that's what they do. On the other hand, there are staked executors, and they're getting primarily execution fees. So they are not getting block rewards. However, the more execution they do, the more they profit from that. And those are like different markets. You need different kind of computer. So if you can run Farmer on Raspberry Pi with USB hard drive, you need like a gaming computer with an SSD to be an executor, right?
And where does the execution fee comes from?
From transactions. So in transaction, there is like there's a transaction itself which occupies a certain number of bytes, and that's what farmers will be paid. And there is some kind of computation like the weight or the gas that executors will take. So that means we can have like millions of farmers and like a few tens of or hundreds of thousands of executors. They don't have to be the same.
That's a big number of nodes. Actually, you mentioned 25,000, I guess, right?
That was non-incentivized testnet. We expect something like 1 million by the time we get to the mainnet.
That's crazy amount of nodes. Okay, another question to Nazar: if Substrate runtime is also WASM, does it mean that for contracts palette we have WASM interpreter running within WASM interpreter?
Yes. Basically, if you have, let's say, 1% of the WASM interpreter, we are dividing that by half because we are running inside of WASM virtual machine, which is WASM time. So that's like half of the percent. That's not great.
But you said that they are very different, right? So they have different APIs.
They have different use cases. They have different APIs. And when the Substrate team that are very productive working on this get WASMer single pass compiler, that should bring that 1% to like 30% or 40%. So we'll like recoup much of that performance penalty at some point. And also you can run that VM in the host and like make a host call to spin up your transaction. It's just like the trade-off that host call versus instantiation time.
But what you mean is that they're different, right? You don't mean that one is better than another, otherwise one would just die, right?
Exactly.
Okay, let me check the chat. Maybe we have questions there as well. No questions. Okay, that was a really good talk. It's good that it's recorded. We can always come back and refresh. Thanks, Nazar. Have a good day. And
thanks for having me.
Stay with us.